Yeah, that's all right.
Or I'll stand over here. How's that? I'll come back.
Right, so our speaker today is Dr. Brad Hutchings, who's a professor in the ECE department at Brigham Young University. In 1993, he founded the Reconfigurable Logic Lab at BYU, and he continues to oversee research there. And in addition to having an illustrious academic track record, Brad has done a lot of work commercially. In 1997 and 1998, he was a visiting scholar at Hewlett-Packard Labs in Bristol, studying ways to integrate reconfigurable computing into personal appliances. And in 2003, Brad was one of 5 people who helped to found Tabula. He presently conducts research in programmable technology at BYU and also continues to be active at Tabula. Brad?
Thank you. So today, I'm trying to figure out what the best place to stand is. I'll try it here. I may move. I wanted the title I finally, after I put all these slides together and tried to come up with the title, was Academic Tools and Commercial Architectures. And with that lead-in, you might ask the question, well, why would you want to build your own tools anyway? For commercial tools, or for commercial architectures, that is. And part of that is that that can be a proven concept in its own right. Hypothetical architectures just don't necessarily account for all the real-life factors. We feel that targeting real chips can be quite important. And nobody writes software for virtual processors. The people who study VLSI, they actually have real parameters there. I mean, most places that do this kind of work actually have access to real devices, and I think it would be good if we did as well. And that's one of the reasons for this work. There are some challenges, though. The FPGA world is generally a pretty closed world. And if you want to actually be able to develop CAD tools for custom devices, or for commercial devices, there are some challenges. The proprietary databases, they've been closed. For years, other companies have really offered to do placing route for them, simplicity and whatnot, for example, but it just hasn't worked out. And once you start getting into real architectures, it turns out the devil's in the details. There's some real challenges there. For us, we had our own personal motivations were 2. One was we wanted to study ways to accelerate implementing things with FPGAs. And so we were interested in rapid prototyping. In particular, what's the shape of this graph look like? Well, commercial tools usually are more over in this space. I'm not saying they aren't concerned about runtime, they are, but the business case tends to push them into more high QOR kinds of things. But there are lots of customers out there who might be interested in a lower quality of result if they could get the result very quickly. People who do prototyping and your emulation people, for example, even places like that are very happy to operate in this space because their customers will just buy bigger chips if, for example, you can consume a little more area. But if you can give them a result that's in seconds or minutes, that's huge for them. And so they're very interested in that. The other one is that for those of you who know Mike Worthland, he does a lot of work in reliability. And so there are a couple of places where he's actually used RapidSmith. We put it together so he could use it for that as well. Probably the more famous example is in space applications, they're worried about ionizing particles coming through and changing configuration bits. That's one thing. But it turns out that it's much worse if it hits a half latch. Half latch is a constant in the Xilinx device. And so if you hit that with an ionizing particle, not only do you change, it's not as bad as changing config bit necessarily, it could be worse, you change a bunch of grounds to DCCs, for example, or vice versa. And so one of the things they did with RapidSmith, which I won't talk in more detail here, is they developed a tool that would actually search the physical post-place and routed database for these half latches, replace them with, say, LUTs or whatever it is they wanted to use, and then rerouted them. Right? Sorry, question? Yeah.
TMR? Sorry? What does that stand for?
Triple modular replication. So this is where you voting and things like that. And that's another example I forgot to mention is that they did a RapidSmith-based tool for doing that as well. Again, because it allowed them to interact with the database. So first of all, I wanted to give you just a quick introduction into XDL. XDL is a Xilinx design language. It's been around forever. It's just very poorly documented. It's not really supported, but it's been there as long as I can remember. I've been dabbling with XDL off and on since 97, 98, and I think it was around before then. It's probably one of the few things in this room that's older than me. Maybe not. Anyway, the idea is that at any point in this flow, you can extract an XDL representation of the physical database. It is a full physical download of the part. Every physical wire, every switch, every let, everything is there. Okay. So there are two things you tend to do with it. Well, we'll just talk about the first one for right now. If you want to take and convert a design at any one of these stages into an XTL representation, this is the command for that. If you want to take and then take, after you've manipulated your XTL and you want to put it back in, this is the command for that. So you can inject yourself anywhere along here. We tend to inject ourselves here at the very last stage, right before the bit stream gets generated. But you can inject yourself anywhere along here if you like. The other thing you can do is generate what's called an XTLRC file. Now, this thing I showed you before was how you get XTL representation of designs. This is an XTL representation of the device. So basically, the entire fabric gets dumped if you do this command. It's a big file. It's 73 gigabytes for the bigger parts. It's a human-readable ASCII file. Now, you think about it. If you describe the part completely flat, and you use pretty verbose ASCII to do it, can you see how a large device would get to be 73 gigabytes pretty quickly? You probably can see how that might happen. So it's, this is a text dump, and I'll show you some examples of it here in a few minutes. As you might guess, it's really hard for tools to use that description, right? And it's missing some information, and it includes a lot of information too often. For example, if you have long wires that span multiple tiles, that gets named for every tile. So you can see where there's a lot of redundancy in there, and then I'll show you how we got rid of some of that. And there are other things where it's just wasn't quite complete enough, and by looking at the report files and doing some manipulations, automatically, by the way, to do that, RapidSmith solves those problems. So essentially, if you go and if you do this command and then you just run the RapidSmith import, then it just automatically generates this in a form that's usable, by CAD tools and so forth. I think if you download RapidSmith, it already has, I think, a lot of the device files already generated for it. So just to kind of get you to an XTL view of the fabric, for those, is anybody, I believe you played with Xilinx. Anybody else play with Xilinx here? So you've probably seen this view before, right? So if we sort of tile that out and show you what XTL's view of that is, it would look like this. And so you've got your CLB, you've got the switch block, and so forth. And everything is done in terms of these tiles for XTL. And if you were to take, this is a view that's generated by RapidSmith. You can see these yellow boxes are interconnect. These boxes here contain the 4 slices for this particular device. And then you've got stuff in the middle, that's where your irregularities are with clock spines and things like that. So zooming in on that a little bit, you actually have an address for each one of these things. So here's your switch box address, and then here is the CLB address. And these are actually the names that you would see if you were to do a dump of the device. It would look like that. And then if you wanted to go in a little more detail, you could see that this contains things like tiles and things if you want to connect to ground or what have you. And then this CLB would contain these 4 slices here. This is a DRAM. It contains the blocks that are shown there. And for example, this is a DSP block. And again, this is a viewer that's generated by RapidSmith that I'll talk about a little bit later. So just so you can state your curiosity about what XTL looks like, this is some XTL. This is for a design. I'm not going to show you the fabric dump. 73 gigabytes doesn't fit very well on a slide. So for example, this is an instance that's named instance 23 that's going to go into a slice L, for those that are familiar with Xilinx terminology, that's within that particular CLB, this particular slice. And then this is the actual programming for the LUTs that are in that slice. Okay. And for example, here's how a net is described. This is just the in pin and the out pin. If we decorate that a little bit further, this would be actually all of the routing in between those 2 pins. Again, everything is there. Okay. So this talks about going through iMuxes, and these are, you can see why these are pretty long, verbose names, but that's what you get from XTL. And we work a lot with modules, and so this is an example. This is the one we had before on the bottom, but this is an example of a module. Modules for us are relocatable hard macros that we can lay anywhere that we want on the fabric. And that's just an example. And so essentially this is the port list that you might see in something like a Verilog or VHDL. And then this is the guts of the module. And of course, they get a lot more complicated than that.
Brad, your relocatable hard macros include routing?
Absolutely, I'll talk about that more, but yes,
They can
absolutely.
include routing.
No, they absolutely, they always do.
They always include routing.
Yeah, they always include routing. So this is, and get back to me if I don't answer that, I will show you some examples, I think. So this is sort of the view of the XDL import and export process through RapidSmith. The idea is that we pull in this very verbose description, and then we provide you with a fairly succinct Java API that allows you to interact with that database in a much easier way. And I'm going to show you some examples. I will show you a placer on one slide of RapidSmith. It's a random placer. It's not all that useful, but it does place, and it does do that. Okay? And then the idea is that you're going to take and hang your CAD tools off this API. If you look at sort of the abstractions over here on this side here with the device, we've got the tiles that are a 2D array of tiles with the tile type and the site where you can put things and wires. And then underneath this you have the primitive type tile. And here within a design you've got instance, net, module, and module instance. So this is a richer description for describing designs. And these are essentially one-to-one represented directly in RapidSmith. So one of the first things we wanted to do if we're going to distribute this so people wouldn't have to have hundreds of gigabytes on their files and could actually download it in a reasonable amount of time was we worked on trying to compress things a little bit, and so the files would load fairly quickly. Chris did a remarkable job. I mean, so for the worst one here, the Vertex 7, starts out at 73.6 gigabytes after he's done compressing it. It's hard to believe that that's not lossy, but once you see XDL, you can see that. So it gets quite a bit smaller, and that means it loads just a lot faster. So if you download RapidSmith and start using it, any of these databases would be about that big, and so you can load them and work with them in a very short amount of time. So let's show you some examples. So first of all, the random placer I was going to talk to you about, I'm just going to put it all up here, we'll just talk about it all at once. So the thing is that you create a new design. You need a random number generator so you can get that high quality placement you're looking for. I'm sure Vaughn's just getting stomach aches over this.
You're not showing a tremendous respect for commercial tools.
No, actually I have a lot, after actually doing this I have more respect, I think. Anyway, the idea is what can you fit on a slide? So the idea is you just have this loop where you get the design instances, you loop across all the instances. If it's, now this is all RapidSmith code that we're looking at here. So you have things like create a design. This is just Java here. This is RapidSmith for getting all the instances in a design. Here you can check to see if it's been placed. If it has, continue. If not, then you're going to take and look at all the compatible sites. So we know which sites are compatible with which primitives that you're going to place. You index through that. If it's been used, of course, you keep looking for a new site while it's been used so far. And then down here is where you actually do your placement. And then you save the file and you're done. Okay? So this is obviously not a real placer, though it will place. But the point is, it's just sort of give you a flavor of the kind of APIs that are available to you through RapidSmith. Okay. Let's see. The other one is if you're going to place a module. I'll just bring the whole thing up too far. The same thing here. So you load in the XD file. It parses the XDL and populates the design object. So here is it's going to take and create a design object coming from that file name. And we're going to take and get this module there, okay? Create an instance of that, find all the compatible sites, and then place that. So this is more along the lines of placing a hard macro. It doesn't show all the details, but again, it should give you a taste of what writing RapidSmith looks like. The other thing that we do in there is we handled, it turns out that that was a pain. I mean, one of the things that's nice is that when I was working with Chris on this to get this done, is I made sure he was trying to use this on real designs all the way along. And so when he hit a real problem, then he'd go back and fix RapidSmith so it worked a little bit better. So one of the things that hassled him a lot was handling ground in BCC, because there's a couple of different ways to do it. You can do it with LUTs, it's kind of expensive, but sometimes you may need to do that, or you can use tie-offs, which are available in the switch box. And so the router needs to partition those nets to use those different kinds of static resources, and RapidSmith provides a static source handler that just holds all that stuff up for you, and you can just grab it and go along. And it gives a bunch of methods for handling that. So it turns out, I had my students use this to write a router, and they certainly, this is actually speeds things up a little bit, eliminates a bunch of detail. Okay, the other one, which I'll show in more detail in the second half of my talk, is a flow we call HMFlow or hard macro flow. And the idea is we wanted to go for really big reductions in tool flow time. What we really were shooting for is, can we get a software model? Can we get seconds for a place and route? And I'll show you some examples of that. We did achieve that. But it's based on creating hard macros. The hard macros were placed and routed using Xilinx software, but then we wrote our own placers and routers to actually place them onto the fabric and route them. And then we go through the regular bit gen process to do that. Here's another thing we did in RapidSmith. That was that thing I showed you before, which is a device browser. So the thing is you load in that XTLRC file number, a physical dump of the entire device. And then once you've got that, you can bring it in here. And it's just helpful to be able to just kind of float around. It doesn't zoom in. You can't sort of see all of the routing in this particular view, I mean, this particular tool. But you can, it's nice because you can look and see what the actual names are used in the XDL. So when you're writing the tool, it helps you to debug things and make sure things work the way you think they should. This is a more of a design browser. So the thing is you find all of the things that are inside a design. So here in particular, we're interested in this particular, I think this is a net, or wire rather. So this is the full name of the wire as it's represented in the original XDL, and you can find out, for example, it fans out one place, it has 5 routing pips on it, things like that. So if you want to find, again, these are a lot of this was tools that Chris developed while he was trying to debug RapidSmith. Chris Lavin was the PhD student who worked on this. This one was a tool that was extremely useful. This was our own interactive hard macro placer. So the idea is that this hard macro consists of all of the elements underneath it, and the idea is you can click on it and drag it around, and the color would change according to the legality of the placement. And then we could also examine the placements that we get out of our own placer. So this tool was very handy for that. In the early stages, the placer didn't do such a good job, and so we'd see if we could do a better job, or in some cases we found out the placer actually did a good job, and we couldn't do any better, and this tool was very helpful for that.
As you move around, Brad, does it actually try to route it in each place? Because you can have some kind of irregularities in the fabric, right? That you can't exactly replicate your original routing at all locations, right? Because you could have, you're crossing a central plot spine or something like that, right?
Yeah, that's a fair point. This particular tool, just we don't show it here. It just shows the routing as fly lines. So this doesn't actually.
Routing.
You mean for the routing in here?
Yeah, the routing within the hard.
Yeah, no, it does check for that.
So it will try to route it at each possible location.
Yeah, well, if the thing we found with the Xilinx architecture that is, as long as you stay, you generally don't want to straddle. I mean, dropping this on a VRAM column would be a bad idea, for example. You would never try and straddle the clock spine. I think it would be illegal.
It won't be able to route.
It probably won't be able to route it.
Okay.
Although I've got some examples where we've actually relocated modules across the fabric to show you the deviations in timing. I'm going to show you that.
So you actually reroute it, or you actually just check the guide?
We just check. We don't reroute it. These things are essentially black boxes at this point that we're dragging around.
What are the different colors? Why are there 3 and not 2?
I was thinking that the same thing this morning. I don't know why we have brown. I think when I use the tool, all I remember is red and green. I don't know where the brown came from. I'm going to assume it's a PowerPoint bug. Good question, though. We also have this thing called a timing visualizer. So the idea is that, again, this is, I told the students to go off and, everybody here familiar with Qt? Yeah, Qt. Yeah.
Library?
Yeah, the Qt library for doing, it's a portable graphics library. It's a great little tool. Very nice for doing, all of this graphical stuff was done in that. There's a Java version of that. And so the timing visualizer, what you could do is you could put in a number here, and then the idea is you could run this scroll bar, and it would show you, these are based on actual routed nets, how you did. So for example, it would be one way, so we'll zoom in a little bit, and then as we zoom in, then we're going to start playing with this number here, and you'll see that some things start showing up red. And so you can find critical paths that way pretty quickly by just playing with this scroll bar. There are better ways to do this. This is I think this project took about a week or so, so just something to throw together. And then, of course, as we play around with that a little bit more, you'll see that we get more red, and even more red as we do that. But this was helpful when we were writing the router, because these routes, of course, were done by the Xilinx tools, but the routes in between the modules were all done by our router. So this was helpful to see where the critical paths related.
So the XTL file does not keep the timing information.
That's correct. I should have said that. There is no timing information here. That's right. So we essentially do our own timing model, such as they are. But there is no timing model in XTL. So strictly speaking, this is not timing driven, at least not in any real sense.
And
I can
for the-
understand why they don't give us timing.
Then for the interconnect delay numbers, you guys are using your own approximated model of that? You
Yeah,
know,
we've
you tried to reverse engineer roughly what the design delays are?
yeah.
Okay.
And then we verified that and we bring the circuits into trace to see how close we are.
Oh, okay.
We need to do a lot more work on that. I don't think we're very refined there. We have kind of a rough cut. And even more a little bit red. And you can zoom in a little bit and you can see, for example, this wire here. It's a little hard to see in this light, but just another example of some of the fun tools that you can do when you have access to the physical database. Okay, so I was going to jump into HMFlow, which is one of the examples. We'll do a more detailed discussion on that. Is there any questions on RapidSmith or XDL at this point? Yeah.
I guess I had one question. Your half latch and your two methods of generating ground in VCC.
Mm-hmm.
So you're saying that, I guess I'm most familiar with Altera's architectures, where you can basically tie off the input to blocks like a LUT with a half latch right at the input, like the last mux. So
Right.
Is that different then? It's basically the tie off is actually in the switch block, you have to run it some distance?
No, I think those half latches work the way you say they do.
Okay.
But the problem is if an ionizing particle hits them, then they're no longer, it takes a while for them to recover. They do recover after a while, but it causes major havoc in the circuit.
Okay, so your alternative is basically explicitly generating rather to all the unused pins, basically.
Yeah, pretty much. Yeah. These weren't known. This was something that was discovered, I think, originally by Heather Flynn at Los Alamos, and, because they were seeing much higher failure rates in their experiments than they expected. And it was because these half latches we haven't talked about much. I think Xilinx may even have software to deal with this now. Yeah?
Quick question, how responsive is that graphical block of mover thing you showed with the 3 colors? Like if I were to take a hard macro and drag it across, so like, would I wait, a fraction of a second or a few seconds for it to finally leave
No,
off the thing?
there's no delay at all.
Really?
There's no lag at all, because there's a black box.
Oh, but doesn't it have to check, like you said, it has to check all the routings inside it?
Well, that's the thing about the Xilinx fabrics. It's extremely regular. As long as you avoid places like the clock spine and things like that, the routing it works. I mean, and that was one of the things we found out is it's a very, very regular architecture. You can put these things, as we'll talk about with the hard macro flow, you can put these relocatable macros just about anywhere. With the exception of avoiding things like the block RAM and DSP. But the tool handles the case, for example, if you've got a hard macro that has DSP and VRAM blocks in it, it does handle that as you drag it around. If you have to straddle a couple of columns to get those resources, it takes that into account. But most of this is computed offline, not interactively. So when you create the hard macro, it goes in a library. There's a lot of stuff that will compute about it. It just becomes part of the metadata for that module, so that when you bring it in, you don't always have to recompute it. But the assumption here, and the thing we found while we were doing this, is that the routing is extremely uniform. Any other questions on XTL? Okay, well, feel free if you have more as we go. So HMFlow was one of the first things that we, sort of big projects that we did with this, and the idea was that we had, 3 or 4 years ago, we participated in a DARPA study about productivity. And the question is, what are the issues of productivity? And there are lots of different angles to attack this. You might say it's the way I capture the design, RTL is way too low level, for example. We went at it from the angle that we really wanted to make it so that designers had more turns per day. This was driven by the idea that when you're trying to debug a system, now there's verification and there's debug, right? Verification is where you run a lot of stuff offline or simulate, and that tells you there is a problem, but it doesn't tell you where it is necessarily, it doesn't tell you how to fix it. When it comes down to fixing the bug, that's usually a single engineer or 2 or 3 maybe doing it in parallel, very focused, looking through the design, trying to find that problem. It's my belief, and I read a few books that suggest this is true, that it's really important when people are involved in that process that you don't interrupt them. So when people are writing, if you think about when you brought written code and you're sitting there doing that all night long, how would you like it if every time you did a sort of a what if, you see if it tickled the code a little bit differently to find that bug, if it took an hour or 2 hours? It's not a linear impact on your debugging time. It's actually exponential, I think. It just kills you. So we went at it from the idea, well, the extreme tends to be like for people that are running on, there's an FPGA-based computer you can buy called Convey. People who are developing designs for that, it's often 24, even sometimes 36 hours for a place and route per chip. Right? Timing closure is very difficult to achieve on that. I got that from Convey. And you know, maybe you can get it less than that, but we weren't even happy with an hour or 20 minutes. We really wanted to say, can we get this in seconds? Can we make this look more like a software compilation flow, strictly from a runtime perspective? And part of this was driven by the idea, you know, when you stand back and you look at how we build FPGA applications today, well, how do we build them? Well, if we were to use a software analogy, when you built your little FPGA app, even if it was a small one, first thing you do is you compile the kernel, then you compile all the standard libraries, and then you finally get around to compiling your code, because pretty much every time when we build FPGA designs, the vast majority of them are ripped up, thrown away, and redone every time, 100%. It's just a tremendous amount of wasted effort, and software people have gone beyond that. Why can't we? So that's kind of what was the motivation behind this. So in terms of sort of the analogy then, we have these large hard macros. They consist of both placement and routing. These are completely independent, usable boxes of circuitry. Think of them almost as if a circuit you could plug into a variety of sockets, you know, self-contained, with the analogy being that that's similar to a software library that gets reused over time. A lot more complex, but similar, I think. So your designs will tend to, like this was an early experiment we did. These were, I think these were multipliers, but I can't remember. Oh yeah, that's right, they're labeled multipliers, done. Anyway, some early experiments we did with tiling multipliers. If you can reuse the hard, all of the effort, the computational effort that went into achieving timing closure, maybe on a difficult module, then you can skip synthesis, all the technology mapping, packing, place and route, all of that is completely reused every time. And so you should be able to reduce your place and route, well, the total implementation time, if you can reuse the effort that came from before. So the thing we wanted to achieve is rapid compilation and high clock rates. We did this in 2 steps. The first step is I told the students, look, I have no idea how well we can do. Don't worry about quality of result at all. Just see how fast you can do the compilation. When they came back and the results were pretty good, and I said, all right, now I want fast compilation and reasonably good QOR. I think I pretty much said for this slide. So the 2 approaches you can kind of see here, the early stages of HMFlow, we did lots of small hard macros. These might be adders and maybe 8-bit registers and things like that. These things, you know, these are big chunks of a MIMO receiver, so correlators and the other parts of the receiver. So these blocks are quite a bit bigger. But we experimented with both. And what we found is that, not too surprising, but the large hard macros compile faster, because essentially you are preserving more of that past computational effort, right? You spend a lot of time and effort getting that macro to run the clock rate that you wanted and fit in the area that you specified. So if we look at this, this pale blue color are the large hard macros, and the orange color is the small macros. So if we look at our run times, right, for the small macros, they're quite a bit longer than the larger ones, right? We do much better on clock rate with the largest clock rate along here with the large hard macros than we did the small ones. We didn't know that at the time. We weren't surprised by the result, but we did both. Yeah?
Okay, just got a question regarding the macro that you had for the large multipliers. How did you preserve the routing information, or how did you extract it and preserve it, and how do you get it to stay constrained within the sort of region of the PGP?
Okay. So, first of all, XTL preserves all physical information. So if I had Xilinx place and route something and exported it as XTL, I get all of that. Physical placement, physical routing, the whole 9 yards.
Right, but how do you get it to stay within that boundary?
Well, the thing is that I'm not letting them place and route it. So once it's been done, then I can relocate it.
Oh,
So I just relocate this module. I'll talk about it a little bit further. In order to get this shape in the first place, maybe that was your first question, we actually use RapidSmith to automatically generate the area constraints for this so that we get the shapes we want. So we can very carefully in RapidSmith control aspect ratio and the area that's occupied by this thing. Does that answer your question?
A little bit.
Well, try again.
Well, that takes care of the placement, but it doesn't necessarily take care of the routing. The routing is still free to sort of pick exceed the boundary of the box.
Oh, I see your question. Sure. So the question is, let's say we took one of these blocks and put it out here, and what would happen to the routing? And indeed, you're right, the routing does spill over. And it depends on how much, so for example, what we do is we take the synthesis estimate for how many slices it's going to take. We use that as our preliminary estimate, and then we'll allocate a ring of area around it. And I've got some more slides on that experiment, but the idea is that gives some room for either the placer, because Xilinx does the placement routing of the hard macro for us.
Right.
But you're right, it does spill over. In general, that's not an issue. You get more spillover when you squeeze it really tight than if you give it a little bit more room to move around a bit, but it does spill over some. Yeah.
Does Xilinx have a constraint that basically will say force this router to stay within this bounding box?
Well, what I'm told is that, well, what the students found that would work is the only way to keep the router from going out would be to actually occupy the routing. So what you could do is you could take and put routing here that's irrelevant, but it would keep the router from using it. Are you well aware of anything else along those lines?
Yeah, there is something like what Vaughn asked about, yeah, you can keep routing in certain boundaries, yeah.
Really? But then you should, okay, I need to talk to you because the students can figure that out. So I should talk to you. Yeah.
One of the other methods too is that you can actually, and it's very laborious, we can go through and put coordinates on every single pin around to prevent it from taking certain nets if we know that it's prone to taking that off, but it's very time consuming.
Yeah, that one, I had heard of that, and obviously with RapidSmith we could automate that. That wouldn't be too painful. Manually it'd be bad.
It also slows down the
Does it? I guess we're not as concerned about that because we threw these over the wall to a supercomputer, as I'll talk about in a second, to do all that for us. I mean, there was the university supercomputer wasn't busy enough. We kept it really busy. I'll talk about that in a minute. So did we finally get through your questions? Okay.
Thanks.
Yeah.
I have a question about your results. The last slide you had?
Here, this one?
No, the
one
previous
before.
one with the compilation time results. So next.
Sorry.
Yeah.
Oh, that was this one.
Yeah, this one here.
Yeah.
So your times are they for the compilation for the whole design?
Yes.
And does that include the compilation time of the hard macros themselves, like from scratch, or do you assume you already have the things in the library?
The latter. So we assume that
Okay.
these have been compiled and placed in the library for reuse.
Since it takes more time to place and route the bigger macros, wouldn't that kind of make this comparison different if you had included that time? Or?
Well, it would probably make it a lot worse, but the point is these macros get used across multiple designs.
Okay.
And so, since this is about reuse, it's a fair point. Given that we placed and routed the macro library on a supercomputer, somewhere between, at the end of the day, we did millions of place and route jobs, but probably somewhere between maybe 100,000 on some of these things to understand, what the impact was on aspect ratio versus the amount of additional area that we placed. So yeah, I mean, if you were to include that, but the goal here was that these are circuit modules that get reused across designs. The other thing to keep in mind, though, in practice, what happens is that once you've got a macro and you're happy with it, and it meets timing closure, you don't need to debug it anymore, then you just keep reusing it in the same design, and it's not impacting your place and route time. It may affect, you might take one of your other macros you're working on and fix it like there, but if it's only 10% of your entire design, then that's going to cut way back on your time as well. Yeah?
How do you handle multiple clock domain crossings if you're stamping out a macro in another clock domain?
Question, let me think. I don't know. It could well, I'm trying to remember now. It could well be that our benchmarks are single clock domain. I'm not certain. Good question. The thing is, though, is that yeah, we'll have to look into. I don't see it as a huge handicap or anything that we need to look into. So, in terms of a hard macro, if it had multiple clock constraints, we'd have to look at how it would fit into the fabric when we did that, and then that would determine the various places you could relocate it, right?
But I mean, like, you're taking one macro in one clock domain, and then you want to place it into another clock domain. It would work still? Or?
Well, the clock domains aren't quite that constrained, right? I mean, there's a lot of clock routing there, and they do have regional areas and things like that, but it's not quite as limited as I think you're implying. Yeah.
Okay, and just wondering about the kind of the problem sizes.
Well, how big these are?
Yeah, well, the number of placeable objects, say, in the case of the small hard macros and the large hard macros, and then
the flat design, how many there are in that case.
Okay, we'll get to that, hold
Okay,
that
sure.
question. At least in terms of, so I'll give you slice counts. We got a slide with that. In terms of, I don't actually have a slide that says placeable objects for small hard macros versus large hard macros, but large hard macros is probably in the order of sort of 15 to 20, and this is probably in the order of a few hundred. Okay, something like that. Yeah.
So for these results, does your design consist of just whatever number it is of hard macros and connections between them, or is there any logic that's been changed beyond that?
These results are reflecting the idea that the hard macros haven't changed, but it does support, you can add logic in the middle if you want. It doesn't have to be a hard macro.
So those results are if you take only hard macros from your library, connect them together, that's how quickly you can place and route it.
Yeah, this is for these numbers, that's correct. So getting to the supercomputer here, there are a couple of questions we had to answer. Number one was, does constraining a module in area negatively affect the timing, right? And the other one, does moving a hard macro around on the fabric affect timing? And so we did this by keeping the University supercomputer busy doing, like I said, it's more like millions. And we generated these really pretty pictures. Hopefully you can kind of see them. I'll explain them, they're a bit complicated. So here is the aspect ratio. So basically, I'm trying to remember, down here I think it's this way and then it goes this way. I can't quite remember which way it went. A student and I went the rounds on this a little bit. But one end was going to be sort of squat and wide, and then up here it's probably tall and skinny. It could be the other way, I'm not sure. This direction is the amount of area overhead. So we would take the slice counts that we get as an estimate from synthesis, and then what we would do is you could add 50% of that, you could double it, you could even add 1.5 times that. And that's essentially that extra ring of area around that. The color represents the timing constraint. So for example, if the timing constraint here I think was for 5.5, and so if you look, most places, if you look at this contour plot, worked pretty well. Not too surprisingly, the extremes of aspect ratio did pretty poorly, right? Because this would be the red color, and so that means that this is like 5.7 nanoseconds or so. Whereas we have this nice color here, or darker than that. This whole area represents areas. So for example, this would have been an aspect ratio of run, so it's square, and you could start out with a 0 overhead, or go across and add more overhead to it. Some of the results we don't quite understand, they're interesting, is that adding too much overhead sometimes causes troubles. We weren't telling it had to use it, but it seemed to slow things down a little bit. Not significantly, we're picking nits here. This was a microblaze that we did for that. So, let's see, this one was, yeah.
So in your library, right, for the which you build for hard macro, do you build a set of aspect ratios, and then because before the integration you don't really know what's the best aspect ratio that you have?
I mean, for the global floor plan.
Okay.
Yeah. No, we only support one aspect ratio. For this, I mean, maybe you would want to do that. We did not. What we were trying to do is make sure.
So there's one aspect ratio, or you have multiple aspect?
Well, so this just shows you one point. We did this for many, many different blocks to get an idea of what a general rule would be for what the aspect ratio should be and how much additional area we should give it. So in general, what we found was, I'm trying to remember, I think it was slightly wider with about a 50% area overhead worked well for most designs. But like you say, it's pretty variable. I mean, you could probably get by with a square on a lot of them, but we sort of looked across all of the different designs we had, and what we found is that particular aspect ratio and a particular area augmentation worked across all of them. So, before this, we had no idea, right? We had no idea whether the aspect ratio mattered. I mean, in hindsight, you look at it, well, that probably makes sense. But before we did this, we had no idea. Was there a particular aspect ratio you needed? In some cases, modules did better wider because they had a variety of, there's more heterogeneous in terms of their resources. They want block RAMs, DSPs, and things like that. So that means you're going to want to intersect more columns, right? But there were other ones that tended to be a little bit skinnier, and so that's kind of a happy marriage between those The other question, of course, is how do we do a timing variation? And so we did the same thing. We basically would place these things, generate all of the information to replace and route. And what we found is that as long as you avoid the center spine, it's only 10 picoseconds. So for all practical purposes, there's no variation at all. Again, not a shocking result, but we needed to prove it in order to, because that'd be the first question people would ask you, well, okay, this relocation sounds good, but what happens when you move things around the park? The answer is not much. So the hard macros, as we've talked about before, preserve all of the routing that's internal. We had to do the routing in between the modules themselves. And so what about that? And so it turns out that we had to do some work there to make that work. So there were a few things that we tried to improve that. We ended up doing a second router, or sorry, a second placer with simulated annealing. Small number of objects, it's still very fast. And then we had a register movement optimization, and then a long line optimized router. Pretty simple stuff. No big deal on the annealer. It just turns out that it gave us better results. We were using Manhattan distance with total wire length as the metric, or the cost function, if you like. So it just gave us better results. Probably a little more interesting was there were a couple of things that are a little trickier. It turns out that, I guess not surprisingly, in hindsight, it's very difficult to deal with these kinds of shapes with an annealing-based placer, probably with any kind of placer, because you're trying to figure out whether this fits here or whatnot. And it turns out that just kills your time. We want to do this very quickly. So we approximate everything as a rectangle. So basically a convex shape that encloses this shape as a rectangle. And then we use that. And then what we did for each one of these modules when they're generated, we add the metadata that says what the rectangle is, and then we recompute all the legal placements for that tool so that it would run a lot faster, whoever asked, but no lag, better information today. And it doesn't take too long to do that, but if you don't do that, then it's really hard to build a fast placer that works with hard macros because their placement's far more constrained. The other thing we did is that these things are registered on their on the boundary. But when you wire things together, it wouldn't work so well. And so we would actually float registers as necessary out of the hard macros directly into the fabric so that we could get better balanced delays by moving the register further into the wire. This helped quite a bit in terms of getting better clock rates. You'll see even with the hard macro approach, there's a variety. I mean, we have large macros, we still have some small ones. Our first version of the router just used lots of short wires. Surprisingly, it's a lot better to use long wires. So I'm just showing you the evolution of the project. You cut the delay in half by making sure you use those long lines. There's a good reason to put those in parts. Okay. Slice counts. Somebody was asking me about slice counts. Yeah. So these were the different benchmarks that we did. And so it looks like the biggest ones were between sort of 8,000 and 9,000 slices. Okay. So I think they're pretty reasonable size things. This is in terms of Vertex 5. This was a system we actually built and deployed a few years ago. It was a big MIMO receiver, and so it was 3 large FPGAs a few years back on these separate boards. This was actually flown. And so this is all code that was working. It was put together in, I think it was a system generator. That's the block diagram tool in Xilinx. And this was done by people while I was still at Taboo. So this is Brent Nelson and his team that was doing this with Chris Lavin, the guy who ended up doing the PhD work on this. Now let's compare it with Xilinx a little bit. So prior to doing those optimizations I talked about, like register floating and doing the things with rectangles and whatnot, in terms of clock rate, this is about what we were getting. When we added those optimizations, we got here, if we take the best of 100, there's a little bit of variance in our tool, we get up this far, and then with Xilinx we do the same thing. Now for the Xilinx experiments, what we did is we took the design, Xilinx just takes it, and we experimented with the Xilinx flow to set the parameters so it was the fastest possible Xilinx implementation. So we tried to at least handicap it as fairly as we could there. So we played with the parameters, so this is low effort and things like that to get the absolute fastest runtime that we could get with the Xilinx parts. And so they would get, right around here. For us, we're right around here. So 250 versus just a little under 200. Now, one thing that's not reflected here, although it's true for the Xilinx as well, is that our population density is usually no more than 50 to 60% of the device. And so replacing these hard macros, that simplifies that problem. So. But Xilinx was running under the same assumptions. Though they didn't have to worry about hard macros, they were just doing the whole thing. So that's what we could get in terms of clock rate. In terms of time, our average run time for 2010 with lower QR, we were right around 12.69 seconds. For the best that we've done most recently with the HTM Flow is about 18 seconds. So you hit the button, it's 18 seconds to place it around your design from the cache. And like I say, our average is about 76% of the clock rate for the Xilinx. Yep.
Is the Xilinx number the place and route time or the total runtime of IC? What is it?
That is the total runtime. It's not just place and route, so that's synthesis and mapping and all that stuff. Now, the one thing that's not included here is that XTL import is slow. So we're doing this all in XTL land, right? To generate a bit stream, we have to take the XTL that we generate from here and import it back into the flow so we can go through the bit stream generator. It turns out if we include the XTL import time, I guess I don't have that slide here. If we include that, we're still faster, but it goes from 50x down to like 10 to 12x because the XTL thing was never optimized to import stuff, and Xilinx isn't that interested in improving it. So, but it's very strange. It's very nonlinear. As the design gets big, or you start using more block rounds, the execution time of the XTL import just blows up. So that's the one downside. So this time does not include that. So it would add time to that if you're doing the XTL import.
One of the numbers that might be interesting to get is the Xilinx runtime with like one lookup table. Because it can be a constant time. It won't be like 10 minutes. So.
Well, you mean just for getting all the files and things like
that?
Yeah,
you have to load in that large routing graph, for example, and you do that even with one lookup table in most tools. So there'll be some lower bound, which you also hit when you import. Like there's no possible ways, or all tools would speed up if you sped that up. It should be not a huge fraction of that 10 minutes, but it'd be interesting to know.
It's actually a good question. Well, in fact, I think I'll go back and ask them to find that for you. So that's a good question. Okay, so the idea is that, remember originally we were kind of wondering what the shape of this looked like. Xilinx is out here for the most part, even if you do low effort and things like that. The question is what does it look back coming the other way? And we feel like we've been able to fill in a little bit of that with the experiments we've done so far. So far it kind of looks like that for our little bit of experiments. Other people may have tool flows that will populate that graph and look a little bit different yet, but at least it's a start. So this kind of approach we think for places, for example, I mentioned ASIC prototyping, where if you're doing emulation, most of the time those blocks are fixed. They're only working on one little block here and there, and they would gladly give up maybe a little bit of clock rate or maybe a little bit of area if they could take and turn this thing around really fast. And so I think it would work pretty well there. The other people we talked to were people like radar people. The radar people were very interested in this because they just have a bunch of modules that they're just always using. It's a standard problem, kind of a domain-specific library. Bring them in, place and route it. And the thing is with radar, they can't simulate it. They want to be able to execute it, so it would work pretty well for kind of domain-specific problems like that. Yeah?
Just kind of revisiting an earlier question, I guess. So how would that curve look if you started changing the content of some of those large hard macros? Like if you made changes within one of your blocks to fix a bug or increase performance or whatever?
It's a good question. I don't know. It would depend on how big the macro is. If it's a teeny macro, it probably wouldn't have much impact on this. If it was a very large macro, it might have a lot of impact on it. We haven't collected any data. It's a good question, but I don't have data for it.
And I guess related to that as well, like what's the flow for that? Is that something you can do inside RapidSmith and have it change that macro, or does it have to go out, generate constraints and run ISE and then pull the result back in?
You could, well, I mean, theoretically you could do it in RapidSmith, but remember, at the end of the day, that's really a netlist. So if you were working with RTL, right, you'd have to go through synthesis and mapping and whatnot to get it back into XTL again if you were to do it there. So I don't think it'd be practical to do that in RapidSmith as it currently stands, because you probably capture it in RTL. I mean, if you're working at the netlist level, it would work okay, but probably not.
Have you tried putting a flat design like with no macros through? And what's the runtime of that compared to the Xilinx tool?
Oh, yeah, flat with RapidSmith?
Yes.
Oh, I see.
Just wondering kind of where the speed up comes from. Does it come?
Well, the speed up just comes from we're doing a lot less work.
Well, I mean, there's that, right? There's,
Alternatively, you could put the macros into the Xilinx Flow instead of having it do flat. Then you're comparing macro placer to macro placer instead of macro placer to flat placer.
Yeah,
Or
if-
flat placer to flat placer, is
Yeah.
Marcel's question.
Oh, so that's what you're trying to say. Well, since we have to add the XTL import and output, we probably do. Our placers and routers aren't that great.
don't include that because that's
Okay.
the fact that
So,
you're
so
not-
then it comes down to our placers and routers, right? And our placers and routers, well, you know, we had one student who did the router, and the router, I give Chris Lavin, the guy who did this,
I mean, there's a heck of a lot of man hours in the Xilinx tool, so I'm not saying like you should be able to do the same. I'm just saying it would be interesting to see, you've got maybe a potential, kind of a lot of contribution is, and to kind of separate them out and see
yeah.
what the quality is of each one of the contributions.
Well, we did break out the contributions of those different things we did, like register movement and going to rectangles and things like that. I don't have a slide for that, but yeah, it's a good question. I'm just guessing they wouldn't probably do that well.
Yeah.
The placer has the least amount of manpower into it because we were only placing a handful of objects, so we didn't burn a lot of time there. The router we burned a lot of time on. It's a maze router. It's not Pathfinder, and it understands the Vertex 5 architecture very well, and so it knows which wires are going to be popular. Things like the bounce wires and things like that that are in the switch boxes. It's very careful that who gets those and whatnot. So it's actually pretty successful. But that said, even so, if there are designs you can throw at this tool, I'm sure it won't be able to route.
So now that you have this kind of infrastructure set up, then hopefully kind of people pile on and improve things, right?
I hope so.
Let's say I just wanted to work on placement,
Mhm.
and I want to now compare my placement without considering kind of the quality of the router that's already there. Can you
Sure.
then go out placement and use the Xilinx router? And
Absolutely. Yeah, that works just fine. The one thing that the Xilinx tools won't do, as far as we could never get them to handle relocatable macros that contain routing. They're always a little fun. And we talked to Xilinx, they could never talk us through and make it work. And so I'm not convinced that that works. But as long as you want to just, if you want to just take and do placement and then run the routing on it, probably know that does work. Yes?
So I was looking at the QR gaps. So the HAL macro that you build use high effort Xilinx compilation. So,
Yeah.
So I would guess the gap comes from really the intra-module, wires and connection
Right,
and
yeah.
things like that. And it seems that the big macro is a route blockage or
Blockage,
obstruction.
right, and then, well, of course, the other thing is we're not getting the module to module, the optimizations that would normally happen across those modules as well,
Right.
synthesis and other places.
Yeah. So I was wondering, is it beneficial that when you do the HAL macro compilation, so you reserve some feed-throughs process so these guys never get routed?
That's a great question. We looked at it, we haven't done anything about it, but I think it makes a lot of sense. Problem is, as you know, we talked about this morning, Chris is at Tabula now, so. As soon as your students get to be really good, they move on, so. So yeah, but I mean, if you wanted to just play around with placement and things like that and experiment with that, I think that would work just fine. Now, in full disclosure, you've probably heard about the Xilinx announcement, the new tool suite, which was internally called Rodan. It's called something else now. That does not support XDL. It does have, we talked to Xilinx, apparently it contains some sort of a tickle interface that allows you to ask questions about the design, and they say that it would be able to reflect the same amount of detail, but they are completely quiet as to whether or not they're going to let us use it. There's no such kind of detail in Altera presently either. I mean, Quip has some things, although when I was over there, I found out surprisingly Quip doesn't support 4 or 5.
It doesn't have a secret variable before. so that, I'm just going to ask them to just open that up. There's no good reason to have variable.
Okay.
I can send it to you if you want.
No, it's fine. I mean, if we ever get to the Altera stuff, at least, so the problem is that the XTL stuff is going to be available in ISE. ISE, the standard Xilinx tool set's not going anywhere. And as long as you just want to experiment with things up to V7, you continue to do this. But just in terms of disclosure, I mean, I don't want to sort of be the wet blanket on RapidSmith, but that's the one difficulty is that XTL is going on. Yes?
I just want to make sure I understood your tool flow correctly. So when you have your place hard macros, and you start doing the register movement to improve your time, those are all done with your timing models, right? At no point are you able to extract that, put it as a netlist with all replacement constraints, feed it back into design tools, and run their timing analyzer on it?
Well, we do run a timing analyzer on our placed and routed stuff. It has to be completely placed and routed to do that.
Right.
But yeah, you can do
You
that.
still can do that.
Oh yeah, my class, I do a class in the winter, and you just finished it, where the students come in and they actually write a tech mapper, a placer, and a router using RapidSmith, and all of the results go right back into the Xilinx Flow, and then we rank them.
Oh,
So yeah, the nice thing is with XTL, you can go in at all levels, and as soon as you get in there, man, it's great. You have access to hundreds or thousands of man years of CAD tool effort on the actual devices. It's very handy that way.
Second question. You had that slide on your clock variance when you moved your macro around.
Yeah.
Just curious, how did you generate those numbers?
The numbers, we did the placement. I mean, basically we did, I forget how many tens or hundreds of thousands of placements. Literally, we didn't try to be smart about it. We just placed those macros everywhere, ran it all the way through the flow, and then collected the timing numbers.
So how aggressive were those macros in terms of the top speed of the fabric?
The top speed, well, the macros themselves were quite aggressive. We did the same thing we did before, where we squozed them and tried to run them as fast as we possibly could.
Okay, so you would have like a macro that would run at, say, 400 megahertz or something like that.
Probably.
And you could still notice only about 250 picoseconds.
Well, that's only the clock spine. It's only 10 picoseconds to be smooth around the fabric. It's a very, as far as we can tell, it's a very, very regular architecture.
Yeah, my experience were way different when I did that. I got the
Really?
clock speed about 300-400 picoseconds when I was moving a block that was optimized to go data flow away from the clock spine.
We probably should talk, maybe, we might have missed something. This is what we found, but I'd be really interested to hear what you found.
What you just were saying there, you're talking about two different things. You're talking about data path delays being well balanced, you're extracting presumably all the data path delays from the Xilinx timing analyzer. You're talking about clock speed. Clock speed wouldn't factor into those data path delays.
Correct.
But it still does affect whether or not you can take a macro from the left side and move it to the right side.
It might, it depends how big the macro is, because your clock speed within the macro is probably still more controlled than that. So.
Oh, thanks for that. Okay, yeah, that makes sense. Any other questions? Yeah.
I've used XCL before.
Oh, good for you.
And then I ran into this problem with encrypted netlists.
With what?
Encrypted netlists. A lot of vendor IP vendors.
We weren't using
give
vendor
away
IP. Yeah.
encrypted netlists. And then as soon as you include one of those netlists in your design, XCL wouldn't get you anything.
Yeah,
I
you're
just wonder if
absolutely
you
right.
come across that or find a way to.
Yeah, we didn't even touch that. Fair point, yeah. I don't think we can do a thing for you with encrypted IP. Maybe the business model there. Yeah, that's fair point. Yeah.
Are these tools and the circuits available academically?
The tools are definitely available. I'll give you the final slide, which you can grab it to. This is the website, and feel free to download. We've had quite a few downloads, and then, as I wandered around, there's somebody at British Columbia that was using it for something, and there's a few people using it in Europe for various things. So it's seen some use. It's not dramatic. The way you know if somebody's using your tools, you get bug reports. That's how you know. If you don't get a bug report, they really aren't using your tools. Every tool I've written that's been used, I could tell. I got bug reports. Dave still was that way. I got bug reports on that. I knew that was being used. So if you download it, the current thing supports all of these things. But like I say, given that Rodin doesn't do XTL, that will be the end of that. So we've been talking to Xilinx a lot about this, and also talking to Altera and seeing if we can get people to open things up a little bit. We'll just have to see. I'm optimistic. I think we'll be able to get something. Yeah.
Are the macros distributed with RapidSmith?
They haven't been, but I don't know any reason why they couldn't. I mean, we could probably, if you're interested, send me an email and I'll see what I can do. There's nothing proprietary about them. There are things that we developed for that project.
Thanks.
Okay. guess in conclusion, I've shown you this XDL-based infrastructure, showed you how you could design some custom CAD tools for it. It's pretty flexible. I've had experience both in research and in a class situation. In the class situation, when we used it, we kept it pretty simple. I had them do for the router, they did a maze router with rip up and reroute. And for the placer, it's just a simple annealing placer. And for the placement, I gave them a fairly simplified grid, but it was still on an actual part, so that when we were done, they could put it inside the flow and do trace on it and see what we're in. And some of them actually generate bit streams and download them, and sure enough, they work. So, most of the stuff I've showed you is more about how to use hard macro stuff, but you can also, it's very good for doing post place and route modifications. You can augment things. I mean, you could do weird things like add models and route them in. I mean, it may not be the optimal thing to do, but if you're doing a quick patch, it could be a good way to get there. We talked about maybe some timing visualization, and I think, you know, as I've done this, it's actually worked out better than I thought. I think having this kind of accessibility is huge. I really think our community is well served if we can get more access of this sort, and I hope we do that. So that's all I've got.
Thanks very much, Brett.